have this structure, we have this kind of joint, this kind of limitations, we rotate a certain angle of degrees, we move certain meters, how will be the output line by n factor, right? So again, identifying your robot configuration is very important. Only then you can start doing kinematic modeling. That's why I spent a bit of time for you to appreciate how can you identify robots. In your exams, they will just maybe if a schematic, you need to identify what are these. Is it a revolute joint, prismatic joint, what's the length, so on and so forth. Okay, so you need to learn to identify these things. Okay. So I will go through, this is a bit about mathematics first. I will talk about vectors and how you represent frames. Now frames will be a very important part of the modeling process. Okay, if you want to discuss, you can go ahead. If you need to discuss, you can just go ahead and discuss. Okay? So we will deal with a lot of vectors and matrices. Right? I'm going to quickly go through the basics and then we can proceed on with what's coming next. And I'll share with you about transformation matrices. Transformation matrices is something like this. You can see it's like your adapter. You go overseas, you have maybe your USB plug. OC maybe is 2 pin. It's kind of an adapter for you to start your electrical connections. But if you look at robotics terms, it's an adapter for you to have your inputs. You go through this transformation matrix, you get your output. You can put it in that sense. So again, kinematics, the first thing that you need to do is identify your robot configuration. What kind of joints that you have, whether revolute, prismatic, right? The distances between these joints. Right? What we generally do is in each joint we will assign a frame. Right? It's an orthogonal frame, XYZ frame. You see this particular XYZ frame, they are always the axes are always perpendicular to each other. Right? And we will stick to this particular convention that we do. So between each of these frames that you have assigned at each joint, you will have a transformation matrix from one joint here to the other joint. Right? And the good thing about this transformation matrix is, after you have identified so-called the matrices between the joints, you can add them together or you can multiply them together. Whatever input you put in each of these joints, you put it in the transformation matrices, it will give you the overall result. Right? This is what the transformation matrix will help you do. Okay? Now in kinematics there are two branches, forward and reverse. Right?
I know.
Okay, if you look at this particular configuration that you have,
two unknown, one unknown.
when you're looking at forward kinematics, you know the joint angles. What you do not know? Sorry?
Displacement.
Final destination. You can put it that way, or your n effector post. Right? This, if you are actually controlling a robot, you will actually input in individual commands for each of the motors. Maybe motor 1, 10 degrees, motor 2, 5 degrees, motor 3, another 5 degrees. And at the end, how will be my n effector position? But this is, because this is so-called in plane, you will get x, y position and theta. Right? That will be your n effector pole. Now, there are, when you input in things in your joints, it's called a joint space. When you are finding your n effector poles, it's called a task space, or the physical workspace that you have. Right? So whenever, if let's say you're reading some textbooks, they say, oh, joint space, task space is actually referring to the input that going to input things in terms of joint angles, it will be your joint space. If you're going to input, let's say, I want to reach this position, but I need to find out what is my theta angle, my joint angles, right? Then you are doing a inverse kinematics. Okay? So this is straightforward for kinematics. By using vectors, you will form up the model which will give you, which will have an equation where if your output, which is your force, equals to a lot of your input parameters, your theta. And if you want to go to a particular location, you know the joint angles to input in, will give you your output. Okay? But for inverse kinematics, what you know is the n factor force. Many times you will have this information. When you're working on a workpiece, you say I want to go from, you're planning a part, I want to go from this point, this point, this point, this point. You don't know the joint angle. All you know is, on my physical task space, I want to go from this point, this point, this orientation, so on and so forth. So this is the information that you have. What you don't know is the joint angles. So this is inverse kinematics. Right? This is the tough one. This one will require more mathematical calculations. Forward kinematics, straightforward. Just input in the angles, you get an answer. It's a direct substitution. If you go through some examples later on, then you will appreciate this better. Okay. As I said earlier, we always assign frames. It's something like you are trying to localize to a particular location. We will always assign, you can call it base, you can call it earth, you can call it ground, but this is one frame you always must assign, right? Your fixed reference frame. So no matter what, this frame will not move. You will be there. But how you assign is up to you. Okay? But it must be consistent throughout. So this frame will never move. Now the second frame is your body fixed frame. Or if you have different limbs which are moving based on the joints, you assign the frames on this link. If the joints move, these frames will move. So you have your fixed reference frame and you have a frame which moves with the body. What you're trying to find out is the transformation matrix which will help you to relate between this frame and this frame. Okay? Take note. So we will rely heavily on how you assign your frames. And again, it will always be this orthogonal shape. It will not be any other form. And there is a reason why. Because of this specific feature or arrangement, you have some properties of the matrices which you don't have to do tedious calculations, so you can find it inverse and forward. Information is easy. Alright, so share it. Okay, same thing. When you are having a industrial manipulator, you will have a fixed reference frame. Now up to you. I can assign this frame here at the base, but as I said, my base doesn't matter. I'm standing here on this floor. Everything is a base. It's a ground level. Right? So up to you. You can assign it here, you can assign it here. But this frame will not move. No matter what the joint do, this frame will always remain fixed. Right? And then what we will do is, for each joint, we will assign another frame. So if you have 10 joints, you will assign 10 frames. Right? So you keep assigning your frames. Now, how you assign these frames, we will talk about it in lecture 5. There is a systematic method to assign your frames easily, and then there's some relations you can just use. And what I will present to you in lecture 5 is not the only way to do it, but that is one of the fundamental approaches. There's a lot of other approaches. Approach is different, but the final transformation matrix you'll get will be the same. Right. Same thing, you will also assign one. Again, every motion that happens, you have to assign a frame because with respect to the ground frame, something is going to move. You need to track this. So you use frame. Okay, but fundamental mathematics, this may be a revision for some, you forgotten about it. Okay. But vectors actually help you to describe a location with respect to a frame. Okay. Let's say you have a point in space here, you have this particular frame here. How do you define this point? Right? You use the origin of this frame. You say that, okay, go by the amount of AX in the x-axis, right? Go by the amount of AY by the y-axis, and then you go up by AZ in the z-axis. This is how you define your position vector. Again, if your origin is not at the so-called ground or the 0, 0, 0 location, you may need to do some offset. Right? So this frame from here to here, actually, what you have is P from here to here, and you're actually minusing off this offset. Okay. Remember our position vectors are the way for everything. That will give you a direction. It starts from somewhere and ends here. If you are going in the opposite direction now, all these values will be depending on. Okay? Because you go up is positive, you go out of the plane positive, you go to the right positive. So anything in the opposite direction of this axis will be negative. That's it. If you want to look at this, if you're wondering why is there a negative P here? So assuming that this P is from origin to here, right? Now you look at the origin of this P. It's now actually at the tip of where my position vector from 0 to point B, point B is here. Right? Now I have to offset this because I am only interested in this vector from this point to this point. But I know the information from this point to this P point, I know the information from this point to this point here, P. Right? So I can use that information to calculate this vector. Okay, no? A break again. Okay, so just look at it. This origin from here to here is P, right? Not this P bar, is a bit different. It's the AX, AY, AZ. Right? I can go directly from here to P, or I can travel from this origin, go to B, and then go to P, right? So it will be this Bx, By, Bz plus this P equals to from this starting point to this end point. Point P that I want. I have one vector which goes here right, and I can represent it as AX, AY, AZ. This is a matrix format. What you see here is a single line. The IJ here represents I is for X, J is for Y, K is for Z axis. Okay. Now I have another point, which is point B. Okay. And it goes from here to here. So let's see. My E is dx, dy, dz. I'm interested in this, right? So I call this P bar first. this fat bar, black figure. So if I look at my P bar, this is actually equal to I'm going from here to here, right? So I can also go from B, then I got this right? So I go B bar plus making sense so far. Can you see the ring?
No.
Okay, then I will use a number. Okay. So what I want is I want to find this. This is actually E bar minus E. Right? Makes sense, right? If you put this back in, you get AX, AY, AZ minus BX, BY. Right? So this is AX, BX, AY minus BY, AZ minus. This represents the I. J, K. These are all unit vectors. Okay? Simple vector addition and subtraction. Right? So it's just P bar by P bar. Because I'm only interested in this vector. Small vector.
老板呢？老板呢？不怕丢，我不怕，我也怕。
So vectors is like that. So again, the ijk represents x-axis, y-axis, and z-axis. These are all unit vectors. Unit vectors means when you find the magnitude of these vectors, they sum up to be 1. Right? Okay. So there's this thing called a vector without scaling and a vector with scaling. It's just for your information because later on when you go to the transformation matrix, you will realize that there's this form which you will see and I'm going to get shocked. So what you can do is something like this, if you look instead of control, it's something like a gain. This scaling is like a gain. You put a particular value, you will enlarge or shorten your vector. Right? So they put it in this format where you can do scaling of the vectors. Right? Now in general, for rigid bodies, as the name implies, your rigid body cannot transform and extend unless it's some joint, prismatic joint, right? So what happens to the scaling? Can you ever scale a link? You cannot extend a link, a rigid link. You cannot do any scaling, right? So you will realize that when you're putting your transformation matrix, this scale will be 1. That means I cannot do anything. You just accept it. Means what you see. Right? If you happen to take modules in image processing or computer science, later on, or if you happen to come across some equations, they will have scaling. Right? But don't touch scaling here. They just set one. Okay. I'm going based on the textbook and your exam, past exam paper. Now, whenever they have a matrix, okay, this will be a matrix, right? And whenever they talk about your first set of column vectors, they will use the notation n, right? So this will be corresponding direction to your move to x-axis. Sometimes in exam paper, they will give you, I don't know, the graphical professor is very interesting to say people. He will give you this values individually, nx equals to some value, ny equals to this. He will not give you this format, he will just give you a whole line of put it in this format and then use this. Okay? So this represents your x-axis, your move x-axis. This represents your move y-axis, and this represents your move z-axis. Right? Your global axis are x, y, z. When you move them, the move frame, you use this as NO. Okay, just take note. I have to stick these notations. If you look at other textbooks, other lectures, they will just use x prime, y prime, z prime. Right? Okay, so just take note of this. Again, in your fixed frame, this is your move frame. Now, what these values are referring to is just the position vectors of these axes respect to the global frame. These are all unit vectors. Unit vectors means when you find the magnitude be equal to 1, we actually need to let's say you have here ax, ay, az, right? How do you find the magnitude of b? You have to ax squared plus ay squared plus az squared. Remember this? I don't remember now, I will remember now. Okay, this is how you find the magnitude of a vector. Okay, when I say unit vector, means this whole value is equal to 1. Then it's a unit vector. So the individual components you square it and add them together in the square root. Yeah, you know now, right? Okay. So again, all these will be unit vectors, but they are just giving you the general direction. Right? In terms of the global frame, these are the general direction. And the transformation matrix helps you to get the information from this global frame to your new frame. Now we are just A vectors. Now let's say you have a point A. How do you handle that? So that's why the transformation matrix comes. Now assuming if you look at this, my origins are the same. Okay? Now, I have shifted this move frame by a distance p. This is what you will encounter in your robot configurations in a method. Right? Your joints will all become at one area, right? They'll be offset, right? If you're going to assign a frame at each joint, then you should take note of the offset as well. So this P is basically your offset between your joints. Alright, you notice this is what you have determined previously. Let's say if you have the move frame in your fixed frame, this is the information that you have. Now if you have another information where you move this, you translate this, you get the same orientation. This is the additional term that comes in the transformation matrix. Right? Okay. Bear in mind this is the position vector from the fixed origin to the move origin. Remember this one, very important. There will not be any other values. Okay. These 4 elements at the bottom, in order always be 0, 0, 0, 1. You get something else, your calculation has some issues. Okay, every transformation matrix will be 0, 0, 0, 1 at the bottom. When you multiply them together also, you will get 0, 0, 0, 1. Later on, I will share with you how to do matrix multiplication. When you go on to the examples, you can verify yourself. Okay? So, take note of this. This is to self-verify whether you are on the right track. Right? Again, why 1? Rigid body. We cannot extend a rigid body, it's there, rigid. Okay? Right, so what happens is this. For this, between this and this, just that if you have a moving object or moving body, this is how you will. Just tell you this in a real scenario, this may be your base, this may be one of your link or one of your joints. And you will assign a frame to these joints. Some offset, you will orientate. This is the transformation matrix that you will get. Right? It will be a 4 by 4. 4 rows, 4 columns. Okay? It will always be 4 by 4. This inner portion is called a rotation matrix because it only takes care of what the rotation of the frames. This piece here will only take care of the translation. Right? Nothing else. So within that 4 by 4, they have an orientation matrix and a position matrix. Okay? They are decoupled, they will not affect each other. You don't try to bring them in.
Rigid body reference, there's a frame reference.
These will be given in individual forms. You need to know how to rearrange them and put it in this form. Okay, what are the types of transformation that we can have? We can have pure translation or orientation. Okay, if it's a pure translation, what happens to the orientation matrix? Will there be any orientation in this pure translation? No. Okay? So later on I will share with you what does it mean by a pure translation. Your whole 4 by 4 matrix will be very simplified. Okay? If it's pure rotation, it will just rotate about the origin. Okay? It will not have any translation. And you can have a combination of these two. You may translate.
Wow, that's fast.
Okay?
So fast.
Right? So just give you the various that you can have. Okay. Now, if it's a pure translation, your orientation matrix is not going to be affected. But in matrix format, okay, wait. Let's say, let me give you an example. Let's say 10. What must I multiply 10 to get 10? 1, right? So same thing. In matrix format, there is a so-called unit identity matrix. They call it identity matrix, but it resembles 1 in numerical terms. Okay? So it's in this format. All the diagonal terms are 1, 1, 1. Okay, I'm just looking at this 3 by 3 matrix. Okay? All the diagonal terms are 1, the rest are all 0. Okay, pure translation. The only thing that you will have is position vector terms. Again, remember the bottom part.
Y-axis and x-axis.
Don't think too much about it. First thing you see, you need to form a transformation matrix are just 0, 0, 0, 1. The rest is. Okay, the way I mark is this. I will try to help you all to get points. If you have something, I give you the points. If you have nothing, I can help you also mark. Okay, straightforward. So, but don't give me a lot of irrelevant stuff. Okay, make sure it's some relevant things related to the question they're asking you. Right? If you really totally blank out, just try to link something.
So what is the something?
Many mistakes people make.
Huh?
I don't know how to solve. I don't know anything. We are not here to kill you all. We are here to actually help you all. So you will help us to help you all. Okay? Okay. So again, an identity matrix represents no rotation. If you have a pure translation, now this D represents translation. Now this is referring to transformation from this green frame to this frame. It's not respect to this to this. Okay, that's why the P is not there. It's just the D. This dx, dy, dz is the element of this D vector. Okay? Okay. This is so-called a validation. Let's say I'm just doing a pure translation. Let's say I put frame to some particular orientation. Then this is what I have. With respect to some Google frame. Right? And that frame, I'm just going to do a pure translation. Right? Now when I do a pure translation, it will be this format. This will be identity matrix, and this will be a distance from so-called the origin of the first frame to what the frame has moved to. Remember that this thing is from the original frame to the next frame. This original frame may not be the base frame. Maybe we have done some other movement before, but it's just the previous one to the next one. Right? The distance is this. Don't mix this up. Right? And what you do is this, when you multiply these two matrices, what you realize is the orientation matrix. Now this represents the rotation of this frame with respect to the global frame somewhere here. Okay. This one is just from here to here, but as remember I was telling you, we have a base frame,
0, 0.
right? And we put in all the values for the respective transformation matrices, right? We can get the overall final transformation. This is the overall transformation matrix that you get. You may have a lot of other transformations. This is just a quick short example. We're going to go through how to actually multiply these one for differential.
下面是最后一个，我都是会100分钟。我还有话吗？你要和谁？
Okay, before that, I will just share with you some basic properties of matrices. So let's say we have matrices A, B, and C. Okay. Now usually to indicate what kind of matrix it is, we will just put some numbers here, 4 by 4 for example. Now, so this represents the row, number of rows, this represents the number of columns. Standard, they will not mix the column and row first. It's always row times column. Okay. Okay, some basic properties of matrices. A plus B equals to B plus B. Provided it must be the same. Let's say you have A 4 by 4 plus say D which is 3 by 3. You cannot end this up. Right? You cannot end this up. They have to be the same size. Okay. about multiplication. Let's say A times B. You can put it times like A, but you can put it a dot. Doesn't matter. Again, they have to be the same sign. Then only you can multiply.
It's not equal A times B equals to it's not equals to B times A. 对咯，但是已经有读过那个 dot 了，骗我们的。
A times B is not equal to B times C.
Yes. I think dot 是 for vector.
You get different
是吗？对对对，对对对，跟 matrix 嘛。But A times B is not equals to B times A， 对不起。那时候是做
Another thing, you may have various multiplications of matrices. Again, for all, we go for I'm using 4x4 because this is what you will go through more. So I'm putting it more specific to your that. Okay. Let's say if you have 3 matrices to multiply. This thing is equals to A times, you can carry out B times C first. You can multiply B and C matrices first. Or is the same as we multiply A and B first and then you multiply C. That means A multiplied with the result of B and C will be the same answer as A times B, the result of multiplied with C. But let's change the order of A, B, C. Once you change the order, now this order is very important. Later on when I talk about motion between different frames.
不然3个小时。啥咪 ？Matrix calculator。我的天，4x4。
Okay. Another thing, identity matrix. Defined by I. 1, 1, 1, 1, and 0.
教我们两个人。
Yes.
教我们。我真的有点想这个。因为比较不了解，我感觉比较不，因为我不想考试。Revision max。
Now again, let's see if identity matrix times A. Remember that 4 by 4 the same size. This is fine. This is also same again. Because it's similar as 10 times 1 equals to 1 times 10. No, I'm not going to use a big matrix, I'm just going to use a small matrix. Let's say 2 by 2 first. So this matrix is A, B, C, D.
2 by 1跟这个是给人的图，它不是这个是不会嘛？因为全都是这样的，就不是有100对吧？就是matrix还是你是
How do I multiply with this?
都是 4x4。
Now, there is a neat trick to know how your resultant matrix will look like. So this is the same type of matrix, square matrix. So it's straightforward. Sometimes you may have some uneven matrix. That one I'll cover later on, but let's do the multiplication so then I'll show you a neat trick. Find your final set of matrix. Now, if I'm looking, if I'm multiplying these two matrices together, now eventually this will be a 2 by 2 matrix again. So you will have 1, 2, 3, 4. 4 equations that you need to find out. Okay? If you look at this, this is the product of multiplying this row and this column.
A times E plus B times
So it will
G.
be
AE plus BG
times
E plus C 大于 BG。我好像会secondary school 下。他不给讲 bracket。没错。
right? You go for the row and you match.
OK 啦，如果
A matches to the E, multiply them
这是
plus
x
B
division，
and G.
本来应该写 division。
Same thing, if you're going for this one, how will it be?
A times F plus B
This
times
row
G,
and this column.
B times H.
Right? So the A times E plus
哈
B times
诶
H.
So it's A times F. A times F.
Hey, sorry. Okay? For this course, you have to do this. Once you start working, you can use software. There's Mathematica, there's MATLAB.
Really using calculator to do it.
But this in your exam will be smaller sizes, so you don't. But we need you to understand the basics.
So 4 by 4 means smaller as well.
Okay? Okay, before we proceed, let's say I have two matrices N, M. This will be, say, 3 by 2, and maybe this is 2 by 4. You can have these matrices,
So you
not
got
necessarily
3 by
everything is
4.
square matrix. Just that for robotics, yes. But for other field, you may have other results. Just for quick general info. If you want to multiply this kind of matrices, you need to ensure, okay, earlier I said that they must be the same size, right? Or else cannot multiply, right? Right, that's for square matrix. Now I have non-square matrix. The only way I can multiply is if the column of this, of my M vector, is the same as the row of my N vector. Or else I cannot multiply them. Because I cannot do the matching between the row and the column. Okay, but this is just a general info. But what will be the resultant matrix size?
3 by 4.
3 by 4. Okay, you will just. Okay, just for info.
So we spend 30 minutes talking about this. Okay 啦，还不错啦，他也没有说是，他比较好。
Okay, so you all can go back and try out. You multiply this row by this column, you will get this value. You can do your own verification. Right?
Sorry, what do you call?
Okay.
Calculator faster.
Now what
I
is
don't know. 记不到。
I want to translate a vector. Just now I was translating a matrix. But many a times you may want to also translate a vector. So what you do is this, because you have some information of your old vector, right? Your original vector respect to the fixed frame. And you have found that, hey, because this point P is translating with a new frame, how do I get the new position with respect to the global frame? Right? All you need to do is post multiply this whole vector with the transformation matrix you found. Okay? Again, we will just be using this matrices to do translation operation of a vector. Right? Vectors usually when you're looking at a point. So let's say I have this whole vector. I am going to translate it in a new frame because I know the information of the translation matrix. The transformation matrix which looks at the translation.
4 by 4, 4 by 1.
Right? So I use this matrix and I multiply with the vector, the position vector.
4 by 1.
Now this information will give you the position vector of this point respect to the global frame after this vector is made. Every information you're trying to do is find out what's happening with respect to global Earth, global reference frame. Right? That's the only way you can send a command to a signal and get to the point that you want. If not, maybe relative to some joint, yes, it's right, but globally it's not matching. Then you didn't really come to the point that you want. Okay? So this is what happens when you do translation. Now, when you are looking at pure rotation, you can either now there are 3 axes you can rotate about. So many a times you will decouple your rotation from maybe theta x, theta y, theta z to maybe just specific values in each of these x, y, and z axes. Right? But what academicians have done is that they have managed to find rotation metrics about each axis and how you want to manipulate later on for you. Right? So let's say now we're just rotating about the x-axis. Now if you rotate this green frame about the x-axis, your A frame will move, your O frame will move by angle theta. Okay. And your P, which is fixed in your green frame, will also move. What you're trying to find out is after this rotation, what is the location of this vector respect to the global frame. Because with respect to the moving frame, it's the same, it doesn't matter. It's like I'm on a turntable. Respect to the turntable, I'm at the same location I'm moving. But respect to the base, I'm rotating actually. Same thing. Right? So you are always trying to find out what's happening with respect to the global frame. Okay. Now because any point that lies on this x-axis, if you rotate, will it change? Let's say a point lies here, let's say a point lies here, somewhere here. If you are rotating this axis, green axis, about x-axis, will the point change? No, right? It will still remain there. So, if you are doing any rotation about, say, the x-axis, the x value will not change. If you are doing anything about the y-axis, the y value will not change. So, same thing for the z. But life is also simple. When you have a robot, you're moving x, y, z, all sorts of things. So they will change. But if you do step by step, you will do with x first, y first, and z, and it will be easier for you to manage. Okay? So this is a quick, so-called mathematical way to find out the rotation matrix of your move vector respect to the fixed frame. So let's say I have this point P. Guys, can we shut it down just a few minutes more after that? Now let's say we have this point P respect to the global frame, and somehow we manage to move this, the green frame about the x-axis. Right? Now in physical space, the point P might be there, but your values on your, look at this. These points represent your position vector of P respect to the moving frame. Right? Also, respect to the global frame, you have some value for this P as well. Represented by Px, Pc, and Py. Now, what we are trying to do is this. We just do simple trigo. You go and mean something I've given you to just to refresh your trigo concept. Now, I want you all, I'm going to end off this soon, but what I want you all by Friday is to attempt to solve this equation. What you want to do is this. My P1, this value here is actually P1 plus P2. I will know certain values now, and P0 is from here to here. I try to find the length respect to some theta values. Find this, break this down component, and see whether you can get it. Then I will go through this with you next week, Friday. How you go about it. Same thing for PZ. PZ is P4 plus P3. But how do I get this P4 and P3? Because from the known lengths. Right? You have to break down in terms of your sine and cosine. Right? Okay? So with that I end today. Try to attempt the exercise questions that I have so far based on what I've done, and then we will go through